Alright guys, so here we have our electron configurations. We'll start off with the rubidium. It's our first one. I'll rotate the camera here. Our first one here. And we have 37, element number 37 rubidium. It's got a electron configuration of krypton 5s1. And we see here's our 5s1 orbital filled. And then we go to strontium, which is our first one that we were really running into that's interesting. So this is the first ionization energy. So since it's the first ionization energy, if I remove this one, it's going to leave a half-filled orbital. So this one's a lot like magnesium, where that if I pull off that first electron, it's going to be a higher energy than what you expect because you're leaving a half-filled 5s orbital. So we come over here and look at our electron configuration ionization energies. Like here's magnesium, it's right there. And I drew a line over here for silver, and it's right there. So if we look, here's element 37, and we ramp up to silver at element number 47, and it's got a fairly high ionization energy. So let's walk our way through these. So we have strontium, 5s2, we saw that. We go to yttrium, and yttrium has a 5s2 as well. It's got one 4d electron in it. So we come over here and we look at yttrium. Here's rubidium. There's strontium, there's yttrium. We have a slight increase in ionization energy there because we have more positive charges in here. Now we have 39 positive charges in here attracting those electrons on the outside edge for yttrium. And these two guys here are in the same energy level, so they're not being shielded. They're not shielding each other. We only have one electron inside here on that D level that's shielding those positive charges, plus all the other crap that's inside there too. But we have that there. We go to Zirc, and we have Zirc has a 5s2. It has two 4d electrons in there, so it has an increase of shielding on the outside with the same number of electrons, but we have one more positive from the proton. And we go over here and we look at element number 40, Zirc, and Zirc goes up a little bit because of that. But then when we look at 41, we look at niobium. Niobium, we have a 1s out here. We have 4ds. We moved we moved those electrons to the 4d electron orbitals, and now they're shielding this more. So these two almost have identical ionization energies because of that. Go to molybdenum. Here we have molybdenum. It has a 5s1 in it also, but we've added an extra electron on the inside plus a positive charge on the inside. So we look at the shielding on that from molybdenum. It's element number 42. Here's element number 42, and it is an increase just a little bit, but not a huge one. So we go to technetium. We expect technetium because it has two valence electrons filled out up there. We have them with 5 on the inside, and we have another one on the outside. We've gained a positive. There's no more shielding that's occurred. So we looked at technetium. We should have an increase in there, and we do. Element number 48. No, sorry, technetium is 43. Element number 43, we see a slight tick up in that because of there. We have the same amount of shielding, but we have one more electron in there. So if we pull that electron off, we have a half-filled 5s, so we expected that to have an increase in electron ionization energy. Ruthenium now has a lot of shielding on the inside, but only has one electron on the outside, so there's shielding that's happening in here. We have another increase in positives. We see ruthenium not to be as great of an increase. Also expected. It's almost the same as it was for technetium. Now I go to palladium. Up here, here's palladium. It has the pseudo-noble gas configuration. All 10 of the 4d electrons are filled in. That's complete. And so we expect to see a big increase for element 48. And lo and behold, I'll get that in focus. 46, 47, 48. There is, sorry, 46 is right there. We have a huge increase right there. And now we get to silver. Here's silver. Silver has an electron configuration like this. It has a pseudo-noble gas configuration on the inside. So all these are shielding. We get one positive more on the outside, or on the inside, and we get one more negative on the outside, being shielded by all the electrons on the inside. And we expect it to see a drop in its ionization energy because we can remove that one, and we do. We see that one electron being more easily removed because we're not mucking around with the pseudo-noble gas configuration on the inside, and it behaves a lot like sodium in that sense that it has a pseudo-gas configuration on the inside and one electron on the outside. We look at the electron configuration here. There it is as an ion, a completely filled 4d orbital. We come down here to look at magnesium. The question is, why is it that magnesium is as reactive or close to being as reactive as silver? We look at the overall picture now and we say, alright, here's magnesium over here. Its first ionization energy is relatively high because it has a half-filled orbital you're trying to give it, a half-filled 3s orbital. If you make it a 1 positive instead of the 2 positive that it normally occurs. So there's an increase in ionization energy there, plus the ionization energy for sodium is relatively high compared to what it is over here for rubidium. So it starts off with more, it only goes up 1, but the overall picture is that with that half-filled orbital removal of that 1 electron and all the step up here that occurs slowly over time with the